Hi everybody, I hope you're feeling good, and today we're going to discuss about federated learning. That's a pretty recent technology that was introduced in 2017 in order to improve the way we train the model into artificial intelligence. So to start, I would suggest that we get a big overview of how classically we train an artificial intelligence model. So we guess you guys are pretty familiar on how is working the training of a model. The more common one is like having a centralized server that's gonna handle all the requests to each devices, requesting the data to train the big model to have a better and more efficient one. So that's a method that works pretty well. That's why it's mainly used. However, there are some challenges like, for example, latency communication. If you don't have any communication, then your model cannot be used, or also the privacy problem because we can access your data with that. So that's why federated learning was introduced. So now let's move on. What is concretely federated learning?
To start, the central server will initialize a global model with its initial weights. The model is then trained using an iterative process. At first, the central server will select a subset of the clients that participate in this iteration and send them the current global model states. Next, each device trains the model on its local data. This data is never transmitted to the central server, which preserves data privacy. Each device sends the updated model parameters that are the result of training on the local data to the central server. Finally, the central server will average these updated model weights from all participating devices to create an improved global model. This process is then repeated until the model is sufficiently trained.
Now that the concept of federated learning is known, we can shortly summarize the commonly used strategies and algorithms to implement federated learning. The most common strategies are centralized federated learning, decentralized federated learning, and heterogeneous federated learning. The most used algorithms are federated stochastic gradient descent, federated averaging, and federated learning with dynamic regularization.
Federated learning has numerous applications across various industries, including healthcare, finance, and transportation. It can be used to enhance features on smartphone apps like next word prediction, facial recognition, image classification, voice recognition, and many others. A model can be trained for these kind of features based on the data that is generated by users using the device. Because smartphones are often on slow or metered connections, it would be impractical to collect all the training data on a central server. Because federated learning is much more network efficient than regular techniques, it can be applied here to jointly train a model on the user's devices themselves. A similar scenario applies to the Internet of Things devices and the self driving vehicles, which have a wealth of sensors to collect data but are usually very limited in their available bandwidth. Federated learning can also be applied in applications where the owners of data are unwilling or even forbidden by law to share data for training with other organizations. For example, banks would like to train a fraud detection model but don't want to share their transaction records with other banks. Hospitals want to train their models to detect diseases from scans but are forbidden from sharing patient records with other organizations without consent from every patient. In these scenarios and using ordinary techniques, training data from a model would be very limited to the data controlled by one organization. With federated learning, however, a model can be trained using all the data from multiple organizations without actually sharing the data with others.
Data privacy is one of the most critical concerns in federated learning. It uses several technologies and principles to ensure data privacy while preserving the model's accuracy. Datasets used by federated learning are always local, which allows to keep data in its raw form, as well as local encryption and the expiration of all data when not needed. Devices do the necessary computations and only report what is needed for this specific iteration of computation by the model. Engineers may only access the combined device reports generated by the devices. Individual device data is never accessed or revealed, and instead only aggregate data is used for the analysis by the engineer and the server. In addition, these generated reports are also immediately discarded after use, which helps prevent data leakage or even unauthorized access to sensitive information. But how do these reports get managed in order to ensure that users' privacy is ensured? Secure aggregation enables the server to combine encrypted results and only decrypt and aggregate. On each device, before anything is sent, the secure aggregation protocol adds zero-sum masks to scramble the training results. All devices that participate in the current round of training do so. When you add up all of those training results, the masks exactly cancel out, leaving behind only their result. Basically, the server can't really see any single device result, but only their aggregate. But of course, this aggregation is still not enough, as the model might memorize these values that it receives. This is why an intermediate step is required to protect the data. This extra step is what we call differential privacy. Data is first pre-processed to ensure that it is suitable for analysis while preserving the privacy of individuals in the dataset. The next step is to add controlled noise over the data. This amount of noise is added carefully and calibrated to balance privacy and accuracy. Once the data has been pre-processed and noise has been added, it can then be queried to extract information by the server.
But there are challenges to federated learning. The main challenges are communication efficiency, privacy and data protection, system heterogeneity, and statistical heterogeneity. The first problem, security, is paramount since the data remains on the devices and privacy concerns are top priority. Although the local data stays on the user device, there is a risk for the information to be revealed from the model updates shared in the network. Luckily, there are some common privacy-preserving techniques that can solve this problem. The second problem we had was communication efficiency. Communication must be efficient to ensure that updates are transferred quickly. This can be achieved by local updating methods, model compression schemes, or decentralized training. The last challenges we mentioned was system heterogeneity and statistical heterogeneity. With a large number of devices playing a role in federated learning networks, accounting for differences in storage, communication, and computational capabilities is a huge challenge. With statistical heterogeneity, the problem is posed by the multiple variation of data present across the client devices. These heterogeneities can be handled by techniques of asynchronous communication, active device sampling, and fault tolerance.
One of the future directions for federated learning is differential privacy, which protects individual data points while allowing for analysis. This can help to further enhance privacy and security. There is also federated transfer learning, which involves training the model on one dataset and then fine-tuning them on another dataset to improve performance. Federated reinforcement learning involves training agents to take actions in an environment to maximize the reward signal. Federated learning on edge devices aims to leverage the computing power of these devices to perform the machine learning task locally. This will reduce the communication overhead and improve the latency. The last future direction we will be discussing is federated learning for Internet of Things, which aims to leverage the distributed nature of Internet of Things devices to enable privacy-preserving machine learning models. Overall, federated learning is a rapidly evolving field, and there are many exciting future directions emerging that aim to enhance privacy, security, and performance while leveraging the distributed nature of data and computation.
Overall, federated learning represents a significant advancement in the field of machine learning, allowing us to train models more efficiently and securely than ever before. Thanks for watching. We hope this video has helped you understand federated learning, its methods, challenges, and applications.